lecture today. So I'm very happy to host Per Lindgren, so professor at Department of Computer Science, Electrical and Space Engineering, well, our department. And it's interesting that Per is an expert in, embedded systems and programming of embedded systems, software development for embedded systems. Well, he will tell way more about himself and his area. And at first, you might think that there is a loose connection to this course, applied AI and such. But apparently, I mean, one of the keywords in the title of this course is applied AI. And AI is not, I mean, I repeat the statement, is not ChatGPT only, so to say. So a great body of knowledge was developed since the beginning of the area, so within logic, knowledge representation and such. And also now, most important topic within AI, or most popular topic within AI, is neural networks. So logic and has branched out and influenced many practical fields. And one of the fields where it found its applications is software development. So we talked during one of coffee breaks with Per, and I thought it's a good idea for you to hear this other perspective on how to use this knowledge that you have gained in this course and see its application in software development. So I stop talking, Per. The floor is yours.
Oh, thank you for your introduction. I think I have met many of you students, or you have met me as well in prior courses. I teach in digital design and microcomputer engineering course, and also in advanced courses in robust and energy efficient real-time systems, design of embedded systems, and compiler technology. So it's a bit of a spread within computer science and embedded systems. My main research interest is within embedded systems, and my background is also into more like digital synthesis and stuff like that. And that also deals with logic, and as I understand, logic has been a big part in your AI course here. And I'm going to give a bit of a perspective from program verification point of view, where we can use program logics and tools in order to verify programs and improve on their safety, security, reliability, robustness, etc. So please stop me if things are going too fast. I haven't given this lecture before, so it's kind of first time for everything. So let's see how that works out. I'm using a bit of material from other courses and research projects that we have ongoing. So if things crashes along the way, don't be surprised by that. I would be more surprised if it actually works the first time like this. So I guess we have a chat window. I will see if I can open that up. It should be under more, like. Yes. So please write in the chat. I also have this menu to the right where I can see if somebody is waving, I guess. But please write in the meeting chat if you have questions, and I will try to monitor that. And also, Evgeny, if you have things that you would like to relate or comment on, please stop me and we'll take it from there.
Sure.
Okay, so let's get to it. So I'm going to talk a bit about the role of formal methods into systems design and program verification. I'm going to talk a bit about logic calculi and propositional calculus and first order logic, also known as FOL. We're going to look a bit at set satisfiability problems and their set solvers and their generalization to SMT. We'll get more into that later. And regarding program verification, I'm going to talk a bit about Hoare logic and what kind of tools you can use based on Hoare logic. That's just one possible approach to program verification, but it's quite heavy in the sense that it requires a bit of theoretical background, and the tools are a bit cumbersome at times. And then we're going to look at an alternative based on symbolic execution, which is much more automated and can be an alternative for people that have no or little or no prior sort of theoretical background into formal methods. So that is my intention, and let's see how that pans out. Formal methods, well, there are many ways to define these, but these are mathematical and rigorous techniques that can be useful for the specification, that is sort of validating that specifications are unambiguous, for example. It can be used for development, and here you can use this, for example, for test-based or contract-based software development. Analysis is about finding errors and bugs and maybe prove properties. Then we are touching on to verification, and that goes for both software and also hardware systems. And in general, one can say that hardware is difficult to change after it has been designed. So this type of formal methods that we're going to discuss now are widely used in the hardware design community because errors are super costly, and also time to market requires that things are right from the get-go. So you can't do iterations in the same way as you do bug fixes when it comes to code. Taping out a new chip might take months to years in the worst case, especially when fabs are heavily allocated, and it might be difficult to get a new run in the fab for generating or taping out a new silicon, a new chip. So there are many applications of this. So you can have it for documenting your design, and to specify it, that was mentioned above. And it can also be applied to improve reliability or availability of systems. That means that the system is online and working. Robustness is that they are resilient to sort of unexpected input. Safety and security becomes even more an issue today when we are dealing with IoT and edge computing, where we are sort of relying on these devices and services to work. So there is a bright future for formal methods because they are really required, and correctly operating devices are sort of assumed, and manual testing won't give any guarantees, and it's very, very time consuming and expensive. So we also need better methods to deal with testing in general. So that's a bit about background to why we would want to have formal methods. So how do they work? Well, there are many approaches to this, but they are in common based on theoretical computer science fundamentals. So we will see logic calculi, in order to express behavior. We need to specify this in some way, so we need formal languages in order to do that. And we need methods and tools to both express our intention and also to solve or automatically, in the best case, prove properties. To that end, we can use automata theory. Applications might use control theory because the application area might be related to control. And of course, this is also useful to program semantics and type systems and type theory. Well, it's both useful to reason and specify programming languages, but we also need them in order to work with formal systems and develop tools in order to help us with this. So it's from both sides. Formal methods is interesting both for example, validating that a compiler is correctly generating code, but on the other hand, you will need a compiler to build tools. So it's from both sides an interesting thing and based on theoretical computer science. So I think you have already mentioned and talked about logic calculi, and propositional calculus or zeroth order logic is the most primitive one out of these that we're going to talk about today. And a proposition that can be either true or false, right? And we can have logical connectives like and, or, not, and so forth. And this allows us to perform reasoning or inference. So we have some premise. If it's raining, then it's cloudy. And then the second premise, it is raining. And then we can draw the conclusion that it is cloudy. And I guess you have exercised this throughout the course. Evgeny, in what way did you look at propositional calculus?
Quite some, so quite extensively. I mean, so we basically considered all the semantics, syntax, and yeah, did the inference. So all the rules that are needed for inference, we went through.
Okay, so you have more of a background in this than me then, I guess. I'm more a user of this. I haven't studied formal methods as a subject myself, so I'm more of a user of this, and so my understanding is a bit shallow at points. But I can see its use, and I'm going to demonstrate some use cases in a bit. So first order logic, it extends on this propositional calculi by introducing variables, and you can also have functions. So you can have a function taking a set of variables and returning some value. And we can reason based on quantifiers, so we can make both for all constructs for a variable or exists for a variable. So this allows us to reason in a more general way. But we also need to define the semantics, that is the interpretation, so that we can also see this as an evaluation of a term. And that together, when we have our term, we can also do deductive reasoning based on that. And this is very useful, for example, to prove a property and you first need to state what you want to prove, and then you can use different methods in order to do that more or less automatically. And when it comes to tooling, of course, automatic provers are preferred, because then you can sort of sit back and relax and let they do their work in the background. And when it comes to use in development, we can even integrate this into CI or frameworks, so that you get your newly committed design to be formally verified in the background and on the Git server, or using some third-party service for doing that, connected to your CI. So it all boils down to Boolean satisfiability. So a first order logic formula is satisfiable if it's true under some assignment of values to its variables. And that holds under a specific interpretation. So you have to have a semantics assigned to your first order logic as well. And in general, this problem is NP complete. And if I recall correctly, this was the first problem that was actually proven to be NP complete. So this Boolean satisfiability has sort of a very strong mathematical grounding and is interesting from that perspective as well. But we are not going to dig deeper into that aspect today. So we can generalize this set problem into an SMT problem, and that is a satisfiability modulo theories. And that gives us ability to reason on, for example, integers and real numbers. We can also reason on data structures such as bit vectors, arrays, lists, and strings. So it depends on what kind of theories that you bring into this the solver that you're using. So there are a big variety of SMT solvers out there, and they support a different subset of theories. And this problem is typically NP hard. And under some theories, it might even be undecidable. And we typically don't want to deal with undecidable problems. So the SMT solvers that we typically come across, these cover theories that are decidable. And an example of that could be Pressburger arithmetic. And we can think of the problem, the SMT problem, as a constraint satisfaction problem, or CSP. And then we can use constraint programming, or CP, techniques in order to solve it. So typically, an SMT solver is sort of a wrapper for an underlying set solver. So it will use the set solver to solve the problem as being Boolean, but they extend the language, so to speak, with integers, real numbers, etc. Then turning it into a primitive set problem and then solve it using a set solver. So that's typically how a SMT solver would approach the problem. Right. So, as I mentioned, there are a huge variety of SMT solvers out there. One worth to mention is Z3. It's developed by Microsoft and considered to be one of the more flexible, efficient, and sort of well-supported, well-documented solvers out there. Bool-Lecter is another one that is much more primitive. It focuses just on bit vectors and arrays, while Z3 has, it has these primitive ones, but they also have more esoteric like lists and stuff like that. Another one that has been around for ages is CVC, and there are different versions of that, 3, 4, and 5, and they have different implementation techniques behind in order to improve. So I guess the latest generation should be the best one, but I'm not sure. I haven't really looked into the efficiency of these solvers. Right, so they all do more or less the same thing, but their implementation and underlying data structures and decision procedures might differ. So performance might be different in between different solvers. So you can't say that there is really a best for all problems solution. There is an interesting one coming up now, implemented in Rust, that has been formally verified, and that is also nice to know that you can trust the solver at least. That is just a set solver, if I recall correctly, but SMT solver could be built up on top of this set solver. There is even a language that is generic to all SMT solvers. So I think it's called something SMT lang or something like that, which allows us to more or less interchange in between different solvers. So you can try the problem with different solvers and choose the one that finishes first. Right, one thing that can be interesting to notice, and I will come back to that, is that we typically have proof irrelevance, and that means that it does not really matter which way you're proving something. The proof itself is not of interest, it's just that it has been proven. By that, we can just kick off a number of SMT solvers, and the one that finishes first with a positive answer, well, then we know that there is a solution to the problem. And how that solution looks like, we don't really care about. Okay, so if we want to use this in order to verify properties of programs, it could be correctness or freedom from errors or particular types of errors and stuff like that. One approach to do that is to base it on Hoare logic. So it's a formal system, so you have logical rules, and which allows reasoning in a rigorous way about the correctness of computer programs. And it's based on the Hoare triple, where we have P, C, and Q. I don't know if you see my pointer. Can you see where I'm? Yeah, okay, great. So P here is a precondition, and we can express this precondition in terms of first order logic, so we can have quantifiers and etc. in the precondition. And then we have the command, which is the part of the program that we want to run, sort of. And then we have the post condition, what should hold after this command has been run. So in the precondition, you also have the initial state or inputs, and the command will affect the current state and generate an output. And in the post condition, we can assert properties of the new state, given the precondition and the command to run. So you can verify, for example, or make statements on the resulting state and the output. And these can be combined, so we can deal with sequences of commands. I will come to that here. Yeah. So this Hoare logic gives you axioms and inference rules for constructs of programming or programming languages. And these are typically sequences. So like a command followed by a list of command until the sequence is finished, for example, and then we have the final state. Conditionals like if then else, loops like while, for loops, etc., function calls, and so forth. And this all is fine and dandy, of course, but if you would need to apply this by hand, it would be super tedious and very time consuming and error prone. But luckily, it's possible using modern tooling to generate verification conditions completely automatic. And these will be expressed as in FOL, first order logic, and then we can discharge these or solve them by SMT solvers. And that will then give us a proof of properties for programs given the precondition. The program itself is the set of commands or sequence of commands, and the post condition is the return value of a function, for example. And the good thing here is that it allows us to abstract away if we have a larger program, we can divide it into functions and procedures, and we can verify these separately. And we can see this as just being a contract for example, a function. So this is the precondition will be the requirements of this function, and the postcondition would be the assurance of this function. So what can you say about the result of the function? So it can be seen as a contract, and then you can do contract-based verification based on Hoare logic, and that's where the real power lies. So we don't really need to re-evaluate or reprove a function. Once it's proven, then we can use the post condition as input for further analysis of code that calls into this function. So the only thing that we need to consider when verifying the function call is that it adheres to the precondition, and then we can use the post condition as the result. So we can sort of do this in a very modular and effective way. Right. When it comes to correctness here, then we have two parts or two outcomes. Either it's partially correct, and that means that the proof or the post condition here that will hold only in case that this command will actually terminate. And termination by itself is known to be a hard problem to decide. So we have the halting problem. You have heard about this before, I guess. So in general, there is no automatic way of proving termination. So this type of approach, if you want to have total correctness, then we also need to guide typically the analysis tool in order to help it prove termination. And this can be expressed in terms of loop invariants and stuff like that. I'm not going to go deep into how that works, but there is no free lunch here. That means that even if we can automate most parts, there will be still some manual things to do as a user of systems or tools based on Hoare logic. They can't be totally automated. So we can also say that we are using an interactive proof system or proof platform in order to tackle these type of problems. Right, so there has been quite a lot of theory here, or talking from my side, but I will soon get into doing some demonstrations, and then it will be clear. Proof of termination.
Okay, so now the sound is good. So it was a bit stammering. So
okay.
Now it's fine. So please.
Yeah. So if we haven't missed something, please stop me and I can repeat it. Right. So there are a lot of tools based on these principles, this Hoare logic, and there has been languages developed in order to express programs directly in the proof language. So Y3 has the Y language. Daphne is both a proof system and a programming language, and they both leverage on Hoare logic. And it's not the only ones. There are a variety of such languages and platforms. Both Y3 and Daphne is able to generate verification conditions automatically and will call into the solver, but it's not given that the solver will find the solution, so you might need to interact with the solver through the proof system platform. So it can be sort of restructuring the information in such a way that it becomes easier to solve for the SMT solver, because that is a MP-hard problem, and we might need some good heuristics and techniques in order to help the SMT solver. And I already mentioned this, that we have this proof irrelevance, so we can do whatever transformations of the problem in order to, as long as it's semantically preserving, in order to help the solver. And we don't really care about how the solver came to the conclusion, because it can be that it's doing like 100,000 proof steps in order to finish, or 1,000,000 or something like that. And you as a human, you don't want to know because these kind of detailed proofs are not what you're after. It's like only the result, whether it was good or bad, whether we could prove it or not. So where can we make use of this? Well, there are many cases where this can be very useful. For example, we might want to prove an algorithm or a protocol to be correct. And this is especially true when it comes to safety or security critical applications. And we can also use that to verify that an implementation actually adheres to a specification. And the way we can do this is by either expressing things or your algorithms or an implementation in a proof language, or we can make a translation from the target language. If you're programming in C or Rust or any other language, you can translate that into Y3 or Daphne equivalent, then prove it, and then we know that the properties also hold for the target program, given, of course, that the translation is correct. So when we are translating into Y3 or Daphne or whatever, system we are using, that we are not missing information from the original program or adding information to the original program that is not really there. So there are some steps here that also needs to be at least validated, but they are typically quite difficult to do. Right. We can also do it the other way around, that we actually formalize our algorithms and implementation in a proof language like Y3 or Daphne, and then we extract into the target language. So we extract C code or OCaml code or Rust code from the formally proven implementation. So both ways are possible, and it depends on the case where what kind of tooling is available for your particular language that you want to use. If there is an extraction process available, or if there is a translation into proof language available. So there is now a quite recent effort regarding the Rust language, where INRIA, a French research organization that is behind the Y3 platform, is implementing a translation from Rust code into Y3, and that is called Creusot or something like that. Right. Any questions so far? If not, I can continue. So we can look at an example using Y3 here. And we can take a very simple case of this implication where we started out from. That was this, if it's raining, then it's cloudy. And we can see that if we just look at the truth table for this implication, then if it's raining, it's cloudy, and that is this one. It is raining, then and we know that then if we say that it is raining and it's cloudy, then this implication holds. That is the way to look at this. We look at this as a promise. And then if we state that it is raining, but it's not cloudy, that's false, because that breaks with this implication. If it's not raining, then it can be either cloudy or not cloudy, and both for both cases, this implication holds true. So it's a bit weird from the very outset, but now we are reasoning here on the implication by itself, not its use, but rather the implication per se. So we want to look at this, how we can prove this truth table using Y3. So now I will change into sharing my screen instead. Let's see how we do that. Share. No, that's not the one I wanted. Let's see where I don't want to share my whole desktop portion of screen. It should be somewhere here. Do you know, Evgeny?
I think you need to stop sharing, and then you click on it again.
No, it was under, I found it. It was under a portion of screen, under advanced. So now we can rearrange a bit the windows here, and I will put VS Code here, which is always the preferred editor, and we can see the code here. So this is, I guess you can see now part of my screen, right?
Yes, but it's a little bit small. If you,
Okay.
okay, but yeah, I guess
Yeah, I
so.
can
One
make
can
it.
zoom this screen
Yeah.
if needed.
Okay, but I can also make it larger like this, right? And what is this? Okay, that's not my intention. Sorry for that. And here we have the Y3 proof platform. I can try to match it to the screen size here, and probably now everything will crash. But let's see. So the same code here that we had in our theory here, the theory file, we have also here, just in a bit easier to read way. So we have taken this into the Y3 platform, and we want to automatically try to discharge these goals. So we set a goal for the platform to prove. So true implies true, and that was our according to this true implies true, right? So we can now run the solver, and we can run Z3 on this, and we see that it turns green. So that means that it was okay. We can try to do this. This should not be provable, because it should be a false here. And let's see how that works out. And we can also see here that after 7 steps, it concluded that this can't be proven. And it's also possible to get a counter example why it's not possible to prove. In some cases, it's not possible. That's when either the solver comes to the conclusion that it does not know. So it could either be that the problem is undecidable, or that the capabilities of the solver is just limited. So it sort of runs out of memory or time. And then we can try the G3, that is this one, and that should be a true, and this should also be a true. So we can see that it was able to prove the properties of implication per se. Right, that's perhaps not so super interesting, but it's nice to see that we can at least prove these trivial things automatically. Now let's look at this arithmetic problem instead. So now we are instead of just looking at the proposition, we are looking at a full logic expression. So we can reason on it. We can do it with just given values like this. This is trivial, so we should be able to discharge that. So 3 plus 5 must be larger than 3, right? And of course, it was able to prove this. Okay. Now let's look at this. Here we say that we want to prove that 3 plus x is larger than 3 for all possible 3s. For all possible x, sorry, for all possible values of for x. And obviously this is not true. And why is it not true? Well, for example, x could be 0, or it could be minus something, or negative. And then, of course, this does not hold. So we need a condition on x here. So now we can use this implication in order to do that. So we said that for all x, where x is larger than 0, 3 plus x should be larger than 3. Can we prove this then? Let's try. Yes. So if we change this, I just want to show that this is no fake. Should we be able to prove that it's larger than 4? I don't think so, because it can be 4, if x equals 1. So this should not hold. And now we can reload this into our prover and try to run this proof again. And then after 122 steps, proof steps, it gave up and came to the conclusion that, well, I can't prove this. So go back to the lab and fix the problem. And we can do that by we can change it by this. It should be larger than 1. Now we should be able to prove it, right? I need to reload. So we can see that it now has been updated. So now we should be able to prove it. Yes. So it works. But maybe this is very trivial and does not really give us the power that we need in order to reason on realistic programs. But it's at least a starting point. So the next thing would be to involve functions here. So we create a function that we call add. And then it takes 2 values or variables or input parameters of type int and gives int an int result. So the type of the result is int and it's computed as a plus b. So now we can make a statement like this: for all x equal or larger than 0, then add x 3. This means that we are applying, it's a functional language, so we are applying x to add and 3 to the result of add x, sort of. So it's a partial application here, meaning that we are first applying x to the add function and then the 3 to the resulting function after applying x to add. And then we want to prove that it's larger than 3. So it's a bit, if you're not used to functional programming, this might look a bit weird, but this is the way it works. So we can reload. I think we already have it down here somewhere. So this is what we see here as the first goal, the goal G here. Yeah, so it was able to prove this. If we, for example, take this away, our assumption here, if that goes away, then we should see that it's not possible to prove this. So we can take it back and reload again. So the language here is designed for proofs. So it might be a bit more restrictive than your typical programming language and have a bit different syntax. But in general, it's possible to translate any imperative program to a functional program. And it's also possible then to generate it according to the syntax of the Y language. So that's the idea, at least. So what we can do here is also we can have 2. In this case, we just had 1 variable. Here we have 2. So we introduce x and y. We say that x should be larger than 1 and y should be larger than 1. So this is our assumptions. And then the implication is that add xy, that is x plus y, should be larger than 3. And here it's a bit interesting. This needs to be larger than 2 or larger equal than 2. This needs to be larger equal than 2 as well. So it needs to be larger or equal than 4, which is larger than 3. So that's the intuition behind this reasoning. So let's do this first, that we already know should be okay, and this should be okay as well. And we can go into here and see that it took 177 steps in order to do this. And typically it's quite fast. If it does not finish within a few seconds, then the solver is probably not able to solve it in any case. So there is a time limit here for 5 seconds. And in order to modularize our proofs, or we can use predicates. So we can make a predicate that add 3 here, taking 2 variables, x and y, of type integer. So you can see a predicate as a Boolean function. So it's sort of evaluates to either true or false. So we have an assumption here and the implication. So now we can use this in order to perform reasoning. So we can, for example, state goal 3 here that says for all x and y, look at this. Here, we don't have any assumptions. We are directly invoking the predicate here, which by itself carries the assumption. So now we can try to prove that. And it also works. And here you can break it down. If it's a complex thing that you would want to reason on, then you can introduce theorems and you can prove them in separation. So it's possible to build up some logic reasoning for more complex problems by intermediate theorems and the use of predicates. And you can also have inductive predicates that are sort of self-referring. And this allows us also to do more advanced types of reasoning. So all clear? Any questions so far? Okay, so let's look at some programs. Now, we don't, in the first example here regarding theory, here we have a very limited language that is a pure functional language. But using pure functional languages, realistic problems or programs might not be that easy to express. So instead, we want to have something that allows us for a more imperative type of reasoning. And even in this case, it's a sort of, this is a functional construct, so this might not yet showcase imperative style programming, but we will get there. For example, in this case, we would want to make a function called inc, taking a variable or an input parameter of type int32 and give something of type int32 back. And now we are dealing with machine integers. In the theory here, we were dealing with, if we go back to the theory, no, why isn't this? Yeah, in this case, we were dealing with integers, but they were of infinite size. But in real programming languages, we don't have that. Typically, we have size-bounded integers. So that's why we're using this mac int 32, which gives us machine integers of 32 bits. And then we have the theoretical integers as well, because we need them for some of the operations that we're doing. So essentially, under the hood, it will use this int in order to perform the addition, but it will use sort of coercion from int32s into logical integers or infinite integers for the arguments to this infix plus operation or infix plus function. And then we are doing the modulus by 10. And now we can try without any contract. So this is essentially the contract. This is the input. If we relate that to what we had with the OR logic, if we go back to that, we saw that we had this P for our precondition, C is the command, and Q the post condition. So this is the precondition, this is the command, and this is the post condition. So if we just try to prove this without any contract, and now we should load up, don't save this, no. So I need to find my way to where this was. Give me a second. CD courses. So here we go. This should be our program. And we can, this is our test add. I will take this away, and now we can reload it because I already ran this session, but I wanted to start it from scratch. So now we should try to prove this. And what does that mean? Well, prove in the sense here is that this will always succeed. So it will try to find whether there are some errors in this code. And we will see here that it will fail. And why is that? Well, here we are doing an operation, the plus operation. And if we don't have any restrictions on the A input here, we might run into an overflow. So this will catch this, and therefore it won't be able to prove the correctness of this function. So we can perhaps try to split this into the verification conditions that it generated. So what I told you earlier, that you're from OR logic, you can generate automatically the verification conditions for correctness. So we can try now and see that, well, there might be an integer overflow. Can there be a division by 0? No, this cannot be a division by 0. That's clear because we are dividing by 10. And what about the result here? As such, well, the result as such, the result of this cannot overflow by itself because it's the result of doing the modulus operation, and that cannot overflow. So the problem here is clearly the lack of requirements or precondition. So now let's try to add the precondition. So we add this. And now we can run SED3 on it, and now we see that it succeeds. So there is no error in this, but we are also not ensuring anything. We are not giving any post condition. So what we want to do here is to give a post condition. So we want to say that the result should always be larger or equal 0. And the result should be less than 10. Can we prove that? Or can we automatically let our SMT solver prove and you can see here now the post condition is shown. So we can try to prove that. Yes, it was possible to prove. But for example, if we changed, say that our intention with the program was that the result should always be less than 9. Let's now try this and see what happens if we reload here. We can see that this did not change. So the platform is pretty smart into caching what kind of proof obligations that needs to be reproven. And it's only this one. And of course here, it's not possible. But what we can do is we can change this into a 9. And we should be able to prove it. And now we see that also we have some changes to the division by 0 thing and the integer overflow and so forth, but this should work. However, it's a bit weird that we put the requirement less than 10 here and less than 9 here. But I mean, it depends on what you want the ink to do. This might be exactly what you want it to do. So now we see that we can do realistic things using the Y3 platform and the idea with Hoare logic. And as I mentioned, it's compositional. So if we have another function that calls into ink, it will look at the guarantees given by the ink function without looking into how ink is implemented. So that's where the power of Hoare logic comes into play. So we're going to go a bit further. And now I'm not sure if I can load another. Now it's a bit restricted, this Y3 platform. Or maybe there was something more that we had in this program. No, it was only this. So we can close this and open another one. No, there you go. Program 2. So similarly to before, we start from a clean slate, open this. So what about mutable variables? Mutability in general is difficult. What we want to do here is to capture these difficulties for an ink that takes a counter, but the counter itself is mutable. So the idea here is that we should update the counter value by the counter +1 modulus 10, similar to before, and then return the counter value. So the return type here is int32. So it's a machine integer as the return value. And now we wrap this into a type with a field count, and we set the field to be mutable. And the field type is int32. So now we want to prove this. And here we have an interesting thing. We have to tell Y3 that we are doing updates to this variable. Right, so let's try do this. We load it into Y3 and we can split this into its verification conditions, and we can try to discharge one at a time. So integer overflow, there is no integer overflow going on here. That makes sense. And why is there no integer overflow? Well, because we have set a requirement to the initial value of the counter. So this would be to the input parameter. So it needs to be larger or equal 0 and less than 10. And see here that now I'm using the logical connective instead of the at, but it does the same thing. So it's just a syntactic thing, difference here. Right, and division by 0 should also pass, right? And integer overflow, well, this int32 value by itself should never overflow, so that's fine. So now we have a mutable argument to our inc. So we can do another test of this, y3 again, and now we're looking at program 3 instead. And I'm going somewhere with this, so even if it looks a bit tedious, we're doing the same thing all over and over again. We want to reach somewhere in the end. Now we are putting our contract not on the function, but on the data. And this is super interesting. So we are talking about the properties of this type. So we are stating an invariant over the type. So the invariant here is that the counter field or count field here should always be larger or equal 0 and less than 10. And we give an example of a possible assignment of count that proves this property. So this by here is just an example that upholds the invariant. We need somewhere to start out from. And now we can write our inc function, taking the counter as an argument. It writes C, but there is no contract here. Instead, this operation will be checked against the invariant. So that means that all operations that we are doing needs to uphold the invariant of the type. And this goes not only for one type, but all types that are associated to invariants. So here we have a different way of arguing correctness for inc here. So what we can do is to reload this. And we can look at, I guess, this one, we can reprove it. So we take this away and start from scratch. And here we have the, this is actually proving this, that this is correct. I guess if we put 100 here, then, oops, sorry. Then it should fail because that does not comply to the invariant here. So we can try reloading this and try to prove this, and then it should fail. Yeah, right. Makes sense. So now we are back with a working variant here. And that worked out. And now we should do this, and we can prove, or we can maybe split VC so it's more clear what we're doing. Now we're checking the different parts here, and we can see also here that it highlights the what are the inputs to this proof. So the proof will involve the inc function and also this invariant. So it sort of syntactically highlights the part of the code that relates to a particular proof. So this integer overflow relates to this part, division by 0 to this, integer overflow also to everything, and the type invariant is for the result, I guess, for this result that it is a correct int32. It can be a bit difficult to read. You need to work with this a bit to get experience. It was a while since I used it. So like that. And this was also possible to prove. This is also possible to prove. This is also possible to prove. And this is also possible to prove. But if we change this into 11, for example, then we'll see that this invariant does not no longer hold. So it should be impossible to prove. So I can try reproving everything, and then we'll see that this type invariant that relates to this is not going to work out. So this is all fine and dandy. Now we have moved the proof obligation, or our contract is moved sort of to the counter, and that generates proof obligations to the inc automatically, to any function that operates on this counter type, or values of the counter type will be exposed to scrutinization. So now we're going to do a real cool thing. I was super happy late last night to get this working, because I never tried it before, and eventually I succeeded into formalizing the problem in such a way that it was possible to solve. So it's a bit of handicraft in order to generate correct programs to prove. So we can maybe do it like this so we see a bit more of the code. So now what we want to do is to show that the counter is monotonically increasing by the inc. But so meaning that the counter value will increase each time you call inc. But we have a limited range of this counter. In this case, we have set it artificially to 10, but it's typically 2 to the power of 16 for a 16-bit counter or something like that. But just for simplicity, I use the limit of 10 here. So we have now an invariant looking like this, where that count field here should be in between 0 and 10. But we also have a theoretical model for the counter, which is a model of an infinite counter. So int type here means that the mono here should not be limited to any specific range. So it's an infinite integer. So we will use this infinite integer to prove that the counter here will be monotonically increasing modulo 10 arithmetics. So here we have this was relating the concrete counter, that is this int32 counter, while this part is relating the infinite counter to the bounded. So what we say here is that the infinite counter should be larger than 0, and this is the mod function, the same as the percentage function, but we have a different syntax here, but that is mathematically the same. Mod mono 10 should be count, which means that the counter should always be the monotonic, unlimited or unbounded counter modulus 10. So this will give us a proof that the counter here will monotonically increase modulo 10 arithmetics. So inc here writes C, and it also gives an assurance that the old C mono value is less than the new one. So we can relate the old state of C here to the new state of C. So that means that the mono here will always increase. And in the contract here, we have said that the counter here should always be the theoretical unbounded monotonic modulus 10. So let's see if this makes any sense to our Y3 platform. It was already proven, so we have to sort of mitigate this and break it down or redo everything from scratch. So let's see if we can prove this invariant So essentially what it needs to do is to check that, well, we can do maybe a split here. There was nothing to split. Okay, what it does is that it will check whether this invariant holds for the initial value of counter equals 0 and mono equals 0. So we can check that. For example, if we did something stupid, like that we say that this is the starting point. Well, do we think that would work? I would say no, because then obviously this invariant does not hold that mod mono 10 equals count. So of course that does not work. So this makes total sense for now, and then we need to reload it. Okay, and then redo the proof. The first part is good. Now we want to prove this inc that it will actually increase by 1. It will monotonically increase, and we do that by this ghost code, mutating the mono timer, and this is the actual code that is doing this modulus operation on the counter +1. So this is the real implementation, while this is just when we are marking it with ghost like this, then it's just a theoretical concept in order to be able to prove this property above and to be able to prove this insurance. We need this ghost code. And if we later want to extract this into real code, in Rust or C or something like that, then all the ghost code will go away. It's just there for the purpose of verification. And the other way around, if you would have a translator from your target language, it could be C or Rust, into Y3, then you need syntax for adding ghost code to your program, but this ghost code will never be part of the actual generated binary. So it will never be run on your actual machine in the end. It's just there for verification. So going with this, we can split it, and we can now try applying the proof system to all of this. Yes, within, it was really, really fast to prove. In this case, that was trivial. Oh, well, 9,500 steps. I got a fast computer, so maybe this is 1,000 steps. 10,000 steps, 26,000 steps, and 5,000. So there is a lot going on here. You wouldn't want to know what SED3 has done in order to find this proof. So it is really powerful. If we go back now, new share, we go back to our slides. Yeah, so what we have seen that we can call this deductive program verification because we are sort of deducing through inference. It's super powerful. We can prove properties related to a theoretical model, but it's also super painful. Coming up with these theoretical models might be as hard as the actual implementation. So in that case, where we don't have a theory that matches the problem, that we have to sort of imperatively build it somehow, then we might not gain much. It's equally possible to make an error in the sort of specification that it will be that you have it in your implementation in the first place. So it is difficult and not suitable to all problems. And you need to become an expert at formal methods in order to work with this. So couldn't we have something that is a bit lighter? Sort of a bridge in between normal testing and deductive program verification. So testing by itself is super hard. So writing tests for programs. How do you know that you have covered all relevant test cases in order to that your program should always operate correctly? Well, in general, it's not possible. It is very difficult. Fuzzing, you might have heard of, or property-based testing. These can help you to cover larger space when it comes to the testing, meaning that it can automate some of the test case generation and so forth. So it can be helpful, but it's never 100%. What we showed here with the Y3 platform is 100%. It is in this case a complete proof for correctness. We are not dealing with partial correctness or any other assumptions. We actually get the proof for correctness of the program. But with testing, it's worse, because even if you get the 100% path coverage, it's still not enough in order to be sure that it's never failing, because the operations themselves can fail. For example, if we have a division by zero, how do we know that we haven't covered the case, all possible cases where div by zero might occur? In a more complex program, this is not possible. And we can't do exhaustive testing, because if we have n number of bits, it will be 2 to the n number of test cases needed, or tests needed, and that's not going to happen. So exhaustive testing is not working. So to that end, we might use symbolic execution. And instead of enumerating all inputs and input state, we will interpret the program and add constraints along each path. And these constraints are expressed in FOL and can be solved by SMT techniques, similarly to what we have seen so far. And the tool for doing this will traverse each feasible path. So it will check if the path is feasible or infeasible. And if it is feasible, it will continue along the path until the function or code snippet will come to an end. So that does not work for infinite programs, for example, that are never terminating. Then the solver will also not terminate, or the symbolic execution engine will never come to a stop. However, along a path, if you come across some assertion violation, then we can obtain a concrete assignment of input and state that caused the error. And that's analog to finding a counterexample to the verification condition in a SMT, for an SMT problem. And then we can be given and replay the original program and find our errors in the code. For example, it will say that if you assign A to 3 and B to 54, then you will end up in a division by 0, and the code will run until you reach the line of code that does the division, and you can verify that it was actually a correct detected error in your program. And you can fix the problem by guarding, for example, checking if A equals 52 and B, or the other way around. Well, for the assigned input values, if then you can just guard your code against that and throw an error message instead of just doing this division by 0. Or maybe there is some other error in your program that it was never intended for A and B to have these values in the first place. Okay, so when you have fixed your code until no more errors is found, then you know the program is ensured to pass all the assertions at runtime. So by symbolic execution, we can know that for any input or any input state that the program will actually pass all assertions. And the division by zero can be seen as such case. So Rust code is excellent for many purposes and also for verification because Rust guarantees memory safety and defined behavior. So at compile time, most of errors are found. If not possible to determine, for example, if an array lookup will be within bounds or a division will be a divide by zero, then the Rust compiler generates automatically assertions. So for example, an array lookup will be assert that I is less than RLN, and then you have your R lookup after that. So that means that this will create a panic in case this condition does not hold. And similarly, if we run into a divide by zero or a division x by y, then it will check that y is not equal to zero. Right. So this is automatically inserted by the Rust compiler, which means that if we are running symbolic execution on Rust code, then we will run into panics, and we can track these panics as errors and report this to the user that, well, your code might panic in case you have these particular input assignments or assignment of input variables. Right. So since Rust is memory safe and guarantees defined behavior and holds with a panic in case you would run into undefined behavior, it's already at the get-go a huge improvement over C and C++. But with this symbolic execution, we can actually prove that all assertions are met, which means that we can prove that we are never going to run into an array out of bounds or a division by zero. And this is much stronger and a leap step improvement regarding robustness and reliability. So, for example, for safety critical applications like medical devices and stuff like that, what if we could have symbolic execution done for this type of really safety critical code? That would be a huge boost in assurance regarding the safety of these devices. So this is what we are doing on a research level. We are looking into Rust and symbolic execution. Is it too good to be true? Well, maybe. If it's too good, if it sounds too good, then it's probably too good to be true. And in the general case, it is, because the SMT problem by itself is MP hard, and we can generate very hard problems to solve for the solver if we have complex data and control flow in our applications. So relating to what type of code we want to validate, SMT problems might be hard. On the other hand, we also have path explosion. That is, if you have code that iterates or recursive code, loops and other stuff like that, then there will be a lot of SMT problems to solve because we are interpreting the program. So if the program takes a lot of cycles to execute, there will be many steps to prove for the SMT solver. So this might run into explosion, and by that we can't in a reasonable time ensure correctness. However, this type of critical code that we are dealing with in medical devices and airplane control and such things, it's typically very simple data and control flow. And it's limited in size. It's not billions of lines of code, but maybe hundreds or 1,000 lines of code. Much, much smaller than general purpose code bases. So we can see that if this fails, either we have two hard SMT problems or path explosion, that means that we will not get an answer from the symbolic execution engine, which is an indication that our code is too complex. So we just go back to the lab, simplify the code until we succeed, which means that we are also forcing simple data and control flow into safety critical code, which is exactly what we want, because we want it to be understandable, explainable, etc., and traceable, and so forth. So this is all for good. So we can actually leverage on the tricky part of the problem in order to improve safety critical code. So what we have done here at LTU is to build a symbolic execution framework called Symex, and it's modular, where the execution engine itself is swappable, so we can define it ourselves. You can write your own execution engine for a particular type of language. And it is a static verifier, meaning that it does not do any approximation. So the result is always exact, unless, well, for cases where it actually terminates. And if it not terminates, then we go back to the lab, simplify the problem, and eventually succeed. So that's the intuition here. So the original design was done by Joachim Norlén, and he did that as a candidate project 1.5 years ago. And now we have had a master student, Erik Serander, who have made some improvements to Symex. And it works now with a different, so Norlén made an execution engine based on LLVM IR, which is the intermediate language of LLVM. So it would work with any LLVM-based language like C, C++, Rust, whatnot. While this work by Erik, he is working directly on the generated binary. So he takes machine code and lifts that into what he called General Assembly, which is a sort of general assembly language, and that is what the execution engine uses for the symbolic execution. And which means that it's very exact to the actual binary. So any errors in the assembler or linker or anything like that would be caught by Symex using his approach. And we can also use that to do cycle correct execution time estimation, because we know for each general assembly instruction, it can be annotated with regarding for this particular assembly architecture, how many cycles does it take to do this or that. And we can also do byte exact stack and memory access validation directly on the binary. So that means that we can assert, for example, that a snippet of code does not relate or refer to any memory that we don't want it to. So we can make assertions that we are within memory limits for the particular code, which is super strong when it comes to safety critical and security critical. So we can, for example, prove that this key store part of where you are storing your secure keys is only accessible by a particular task or function in the system. And no one else can ever reach this location, which improves hugely the security of implementations. Right, so I think we're running out of time. We already use Symex in courses in this robust and energy efficient real-time systems course. They are playing around with Symex, and it's a research prototype here at LTU. So we're using it in various research projects. For example, we are going to look into root of trust bootloader. Oops, sorry. and doing schedulability analysis for Arctic applications based on a symbolic execution of machine code or generated binaries. So your contributions here, it's a very active research going on here in connection to Tampere University. They sit on a lot of competence when it comes to hardware. So we are doing software hardware co-design together with them to improve the safety and security of next-gen RISC-V processors. And they are actually taping out these through TSMC and get real chips out eventually. So that's pretty cool. Okay, for those that want to hang out for a bit, I will run some demo of Simex, just a short one. For those of you who have other duties or want to leave, that's perfectly okay.
Just Per,
Yes?
one thing. Those who want to leave but still want to participate in a discussion about midterm, so you stay anyways.
Okay, so I will keep this short, the demo. If you want to if you have questions, you can always reach me through mail or Discord or Telegram or Signal, but you will find me with my full name. So, right. So I will stop sharing and I will make a new share of my desktop, and we will have a very quick demo of Simex. So I will close this, and here we have Simex code. We want to analyze, let's take this away. Nope. And let's see where I got this. I need to find my one of my 1,000 different windows that I have open. With a bit of luck, I think this should be the one, right? So this is a snippet of embedded code running on a Raspberry Pi 2040, which is a Cortex-M0 based processor, or actually a dual core processor. And it's quite interesting from embedded perspective because it's very, very cheap. You can buy them for like 7 kronor, 7 crowns in volume. And you can buy a dev kit. I will show you. I have a few of these, and this is the processor. Well, I'm not sure if you can see this, but in any case, this is the processor, and that's all you need, more or less. You need an external memory for it as well, but that comes with the dev kit, and it's only 50 crowns. If you want to play around with it, you can find it on a lot of web stores. This is Rust code. We have a function here with named getSign, which takes an input i32 typed v value, and it will have a condition execution here. If v is larger than 0, then it should return a 1. If v equals 0, then it returns 0, else it returns -1. And now we can write cargo Simex, and we should be able to, I will check what is the, getSign. We can take this, I guess, as a input line so that I get it right. Cargo is the build system for Rust. Simex is our tool. We tell it that we want to look at an ELF file. We tell it that it should run example1. And inside there, we are looking for function getSign. And then we can optionally compile in release mode. And now we can run this. I'm hoping that it will work. Yes. So the results of this symbolic execution is shown here. And this is the input value V, a 32-bit input. So it has found that given the input value 1, then the result will be 1. So now we can check that to our program specification or our actual implementation. So if it's a 1, then it meets this condition, V is larger than 0, return 1. So it found that. Here it says that if the input is 0, then the output is going to be 0. Does that comply? Yes. If V equals 0, then return 0. And now, finally, if we have a negative value, then we will return -1. And for those of you who recall the digital design, this is a 2's complement representation of the value -1. And this is the minus infinity or max value, negative value that you can find. But it's not given that this is the only input assignment that triggers this path. It was just to show that, well, it gives an example. For example, we could say that we are returning 2 here. And then we can run cargo simex, and we should find that, let's see, if we equal 0, then we are returning 2. If r 0, maybe it did not recompile correctly, because I would have assumed that we would have a 2 here, but for some reason it does not seem so. Let's see if I can. Let's see. There might be something weird going on here. We can try in release mode. Now it does a lot of things in the background. So input assignment 0 should return 0. I'm not really sure why this does not, it's not what I expected. I would expect this R0 to be a 2 here. For some reason, it's a not. R1 here, that was the negative. No, this is the -1 for an input of 1. Maybe we... No, I can't see exactly what went wrong here, but the idea is that it should work. As I mentioned, it's a research prototype, so something might be, I might have done something wrong here, or that the tool is in stable condition right now. I will check with Erik and get back. But if you are interested in playing around with Simex, it is available, and you can just download it. I can show you where you find it. It should be on GitHub. And Simex. A second. Yeah, here you go. I will copy this into your chat, and if you're interested in looking at this. And there is a particular branch here, ARM v6m, that we were using for this example because we are symbolically executing ARM v6 assembly, which is the assembly language for this Cortex M0 processor and the Raspberry Pi 2040 dev platform. Right, I think I will stop there. It was a bit confusing at the end with the example.
Not at all, Per. So I think it's a research project, and it just shows opportunities to students.
Yes,
no, really,
always room for improvement.
Absolutely, and I would say, I really am thankful for this class. So it was really great. So really, I would say it's like a cherry on top of the cake. I mean, for this course, showing the practical applications.
Yeah, thanks for having me. And if you're into doing master thesis projects or in-depth study projects at LTU, just approach me and we'll come up with some crazy ideas to work on this. Maybe fix this bug, among other things.
Yes, but thank you once again, and I think it's really a great conclusion because we consider it. I mean, different logics. I mean, starting from this zero order to first order to fuzzy logic to description logic, so ontologies and such, and now so we see this application of for logic to practical problem. I think it's really great. So it gives a kind of wider view of the area and its applicability to real problems. Yeah, so Per, once again, thank you. So if you have something else to do, so you feel free to disconnect. Otherwise,
yes, I will do that.
I will just say a couple of words to students, and that's it.
Yeah, see you around.
See you. Okay. Hi, all. So let me do this. I want to answer some questions, some typical questions that I saw in Discord, and then basically I will comment on some cases about missing points, and finally, so maybe you have other questions for me to ask. First, I just want to say aloud once again, so I have written it already, I mean, after first occurrence of the issue. So there was a problem with pasting in the images of graphs. I understand that, and so my response was that I will generate, or I will attempt generating these graphs myself based on the RDF statements that you're supposed to write in the code in the answer field, and then if I fail to generate graphs just by copying and pasting into and doing these different transformations, then it will be an indication that something is wrong. Yes. Next, so there were some questions about this particular problem, I think. So a correct statement, a Sparkle statement to get people with both fields, has daughter and has son. And as I just want to refer to Discord, so somebody, I mean, one of the comments was really right to the point. So none of them is correct. Well, some of you have mentioned periods. Well, that's also a problem here, obviously. But before all this, I mean, this logical stuff in the where statement, which is not really working well in Sparkle. So you would need to do filtering. here. Or no, not filtering. Sorry. Yeah, so you need to construct a proper where statement without logical operators. So no filtering. Yes, and next, so that was a question, and again, so it was I agreed on Discord that having is the correct clause for grouped or ordered queries. So it will be regraded. So with having as a correct answer. Then and finally, so it was one question. So that was okay, I guess. So a question about this problem over here. So consider the following logical expression, blah, 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 blah. Which of the following expressions describes statement? Gruyere is a kind of water. Well, the correct answer is here. And I have to say that it's, well, this question was formulated in this way on purpose. So the actual question is the second part. So it's really disconnected from the first statement. So it has little to do with it. Moreover, the yeah. No moreover. So basically, the question can be answered just without any reference to this first statement. Okay, then that is more or less it about quiz 2. So it wasn't too much complicated in my eyes. So any questions? Yes, please unmute yourself and speak up so that I don't miss any hands.
Yeah, I argue that you can use filter as well, because then you will like filter the values in
Yeah, you mean
the
here?
number. Yeah, because you would.
Yes, saying that it will be great. I will leave the filter answer intact. So all the filter answers will remain being correct.
Okay, great. Thank you.
Okay. Anything else with respect to quiz?
Evgeny, it's me again.
Yes. Yeah.
I got it working. I was in the wrong folder. So the thing was that we were not editing the file that was actually run.
Okay.
So I can just, it takes 20 seconds, and I just want to share my enthusiasm
Okay.
to this problem. So I will share my screen.
Yeah, I need to stop sharing. Yeah, so go on.
Let's see, and under advanced portion of screen, and so that I guess now you should be able to see the part that of the code that is actually the one that we were running. So we have the test case down here, and we can change this to a 5, for example. And now we should be able to run it. So I'm running cargo simex on this particular function, get sign, and we see here for the input assignment of 0, now it finds that the output value is 5. Just to show that there was nothing wrong when it was just me being in the wrong folder.
Great. But we believed you in the first place.
No, you should not. I mean, if you can't show, then it's a no-go. Right. So I stop sharing and leave you to it.
Yeah.
See you around.
Yeah, thank you, Ben. So then the question is regarding some missing points. So if you, so I first will check how many people will miss how many points, and towards the end of LPE, so maybe first week of January, or so. I will inform you about a possible makeup test or quiz where you could compensate for missing points. So only, I mean, I will consider only the cases with the reasonably kind of low delta to the passing limit. Any questions on that part? Or any other business that you want to bring up?
Can you please repeat the last point? I couldn't hear you clearly. Sorry for that.
You mean about the missing points?
Yes.
Okay, so if it's happened that by the result of 2 quizzes, you scored less than a passing grade, say less than 150 points. Say you scored what can be reasonable, 130 by some reasons. So I will consider these people to do a makeup quiz during the last week of teaching study period, which is first week of January or second week of January. And we'll give you a possibility to to gain the missing points. Is
Thanks.
that clear, Junior?
Yeah, thank you.
Okay. Any more issues? Well, if not, then I think, well, I did a quick check, so you did a great job in both quizzes, and the lab 1 is getting graded. I mean, you should give us a little bit of discount so that we are 2 and the course is quite large, so we need, it takes time to check all the implementations. But so all grades will be available in time. So I mean, before the next study period starts. All right, last chance for questions from you. So unmute yourself and speak up.
Yeah, if I can ask, the way that you are grading this subject is based in the points in the midterm, or would you take in account also the labs and the assignments?
Okay, can you say again, please?
Yeah, so I wanted to ask how it will be like the final grade of the whole course,
Yes.
because in the Canvas page, I think that you only take into account the grade of the midterms.
No. I think
No. Okay.
it's no, it's not grade of the midterm. So let me share the screen and check, just not to be too verbal. Courses. So let me see. Canvas modules. Oh no, I think it goes to home. So you have a submission assignment as well. So here is the grading scheme, you see. So labs needs to be passed, and you will be graded 3, 4, 5 for the home assignments and for the quizzes. And basically, here is the way how the final grade will be calculated. Does this clarify stuff?
Yeah, but based on that, what I understood is that you have two grades for each midterm, or is it like one for the home assignments and one for the midterms, and then you just
I'm not sure if I understand what you mean. So midterms are graded separately. So 2 midterms you need to score 150, at least 150 to get 3. So both midterms will be graded 3, 4, 5, and then home assignments will be graded separately. So they will also generate 3, 4, 5.
Okay, I get it now. I was confusing yes, one thing.
Yeah, no worries. I mean, so feel free to ask if you are in doubt.
Okay, thank you.
More questions, guys? Okay.
I do have a question.
Yeah.
It's maybe a bit on the philosophical side of things.
Yeah.
It's about the first order logic in Gödel's incompleteness theorem.
Yes.
I was thinking, how does that affect?
I see if I can
Yeah.
respond in
Yeah.
Yeah, sure. Go on. Sure.
Do you think that it affects a logical system, like in computing, especially AI systems, that there could be statements that are true, but we cannot prove them according to the axioms that we have? And that's what I understood about this incompleteness theorem.
Oof, I guess I need some time to give you some
Sure.
more grounded response. Can you send this question in Discord?
Yeah, I can surely. Should I put it in the journal chat?
Yeah, you can do that, yes.
Yeah, for sure. It would be nice to have some
Yeah.
insight from you on this. Thank you. Thank you so much.
Okay. More insights? Well, if not, then it's time for lunch, I guess, for everybody. So thanks for joining today. So see you next time. Bye.
Thank you.
Thank
Bye.
you. Bye.
Bye.